We are about to see our last test. Isn't that exciting? Woo, woo, woo. No, it's the root test. Okay, I apologize for that. The root test has three statements, just like the ratio test does. It also uses a limit expression, and we're looking at the limit as n approaches infinity of the nth root of the absolute value of a sub n. So this test will apply to terms that, a series that have terms that are both positive and negative. Well, we just won't put the negative into the root. This is a little weird though. The n exists as an index of a root, and it's going to go to infinity. How does that work? You'll see how it works as we do our examples. If this limit is equal to L, well, we can call it L, and what we care then about again is whether L is less than 1, greater than 1, or is infinity, or equal to 1. If the limit is less than 1, then the series is convergent. And of course, we mean the series sigma a sub n. If the limit is greater than 1 or is infinity, then the series is divergent. And if the limit is equal to 1, then the root test is inconclusive. And right now, we're going to make a note. If either the ratio test or the root test is inconclusive, then, well, that means use a different test, but then so will be the other one. So if I use the ratio test and I get a limit of 1, I do not then go use the root test. I will again get a limit of 1. That means just try something else completely. Let's look at cases where the root test is indicated. Aside from the fact that the instructions tell us to use the root test, I tell you I'm not going to tell you what test to use on an exam. You're going to have to know what test to apply. That's part of the difficulty of this chapter, right? Here we have the sum as n goes from 1 to infinity of negative 2 to the n divided by n to the n. A lot of times, not every time, but a lot of times, folks, if I see an exponent of n, especially if I see an exponent of n for every base that you can see, then I want to use the root test. It's going to look like this. The limit as n approaches infinity, and as we said, for the root test, we're using the absolute value of, or the absolute values of the terms. So I'm not going to include the negative 2. I'm just going to write it down as the limit as n approaches infinity of the nth root of 2 to the n divided by n to the n. Now, folks, we have an n index and we have n exponents. They will cancel each other. And so we end up with the limit as n approaches infinity of 2 over n. That's why the root test is indicated when you have an exponent that looks like n. As n approaches infinity, 2 over n goes to 0, which is less than 1. So the series is convergent. And of course, we used the root test. So it's convergent by the root test. Folks, remember that for the limit comparison test, if I get an answer of 0, then it becomes one of our special cases. And I just want to underscore a difference between the root test and the limit comparison test. If it's less than 1, we're good to go. So make sure you have those distinctions down. One other thing, folks, in our numerator, killing the negative, right? Just considering the absolute value, we have 2 to the n. That is an exponential, and those things grow really fast, right? In fact, an exponential will grow faster than any polynomial. In the denominator, we have n to the n, and what we see is that the limit turned out to be 0. So by testing this particular series for convergence, we've learned something about exponentials versus n to the n. And what we've learned is n to the n will grow faster than any exponential. If you look through the examples that we've done, or the homework that you're going to do after you've done it, right, then what you'll find is that a polynomial like n cubed will grow fast, but it's going to be not as fast as 3 to the n, an exponential. And neither one of those grows as fast as a factorial. And none of them will grow as fast as n to the n. This is just an aside. You don't get to write down on a test or anything Well, the n to the n grows faster than the n factorial because you said so in a video. You have to perform the test and show me all the steps there, okay? Let's look at another example though. We've got the sum as n goes from 1 to infinity of the quantity negative 2 to the n divided by n plus 1 to the 5n. Now here I see the exponent is 5n, but there's an n in the exponent and the whole thing is the base, right? So that's where the root test is indicated. Please perform the root test. Come back when you are done. Putting the absolute value of our expression into a limit statement and a root statement, we've got the limit as n approaches infinity of the nth root of the quantity 2n over n plus 1 to the 5n power. As we saw before, the n index will cancel the n in the exponent. Yay for the root test there. And so we have the limit as n approaches infinity of the quantity 2n over n plus 1 to the 5th power. Dividing out inside the parentheses the largest power of n that appears in the denominator, we have the limit as n approaches infinity of 2 over 1 plus 1 over n to the 5th power, and as n approaches infinity, 1 over n goes to 0. We're left simply with 2 to the 5th power, which is 32, happens to be greater than 1. We conclude that the series is divergent by the root test.